Hi, this is Tom, and in this lesson we're going to learn about what's called the change of base formula. And before we do that, we're going to do a little bit of work. And it's not much, it's actually some work that comes in handy to make our lives a little simpler that we may not really recognize without it being shown to us. So let's go back to our very beginning where we said that if we have something like y equals b raised to the x, then we know that we have the logarithmic equation of log base b of y equals x. So with that, I want to evaluate a few that come up regularly that we really want to be aware of. And the more aware of it, then the easier it is for us to work with logs, and we can figure out the change of base formula. So here we go. The first one I want to look at is if you have the log in some base b of the number 1, what would that be? Well, let me use an x there, of x. Well, we know that if this is true, I probably should have switched the order of these, but that's okay. We can write it as the exponential equation b raised to the x equals 1. Well, any number raised to what power always gives you 1. And the answer is when x is 0. So whenever you have the log, regardless of the base, when you have the log of 1, the answer is always 0. All right, let's try another one. How about if I have the log in base b of b? What is that going to give us? Well, let's use our if and only if. We know that this means we write it in base b to the x equals what we're taking the log of. Well, we're taking the log of b. Now, notice we don't write it, but there's always an implied exponent of 1 if you need it. So this is the same as saying x equals 1. So if you're taking the log of any number of which you're already in that base, then the result is 1. And maybe a numerical one might look easier. Log in base 2 of 2, since these are the same, this is 1. Or here's another one that may not be so obvious. What about the log of 10? Well, remember, when you write log without a base, the base here is implied 10. This is the common log, and so this is 1. Or there's one more for us. What about if we take the natural log of the number e? Well, remember the natural log is in base e. So we know that this is just 1, and we don't have any calculating to do. There's one more we're going to need. That's this. If we have the log in base b of b raised to some power, how about x? We'll use n. How about n? B to the n, this equals x. Well, let's go and write our equivalent exponential. This says that b raised to the x is the same as b raised to the n. That's strange. In other words, x equals n. So what does that mean? It means this. If I have the log in base 5 of 5 cubed, then all I have to do is the answer is just the exponent, 3. That's what it's telling us. So that we're going to use those few properties, and now we're going to learn about the change of base. But I want to give us an argument for it first. And here's how we're going to go about doing that. What I'd like you to do is, in your calculator, if I asked you to take the log of 2, you could. And so let's do that in our calculator here. Here we have, let's take the log of 2. Now this calculator actually has log base 2, but traditionally it's just log of base 10. So if I take the log in base 10 of 2, need a parenthesis, I get an answer of, oh, whoops, I have an extra parenthesis. I have 0.301, and that goes on for a long, long time. So let's get rid of that. We have 0.301, and the number continues forever. We have the non-repeating pattern. But what if, oh, and here's another one. What if I asked you to take the natural log of 5? Well, let's go back to our calculator. And we can do that too, because the natural log function is down here in the bottom. We could take the natural log, 5, press enter, and we'd get 1.609, and that goes on for a long, long time. So let's come back here. Oh, whoops, I wanted that one back. This might take us a bit to get back. Okay, so if we're here, the natural log of 5 we said was 1.609, and it keeps on going. But what if I wanted you to do this? The log in base 5 of 10. Well, it seems simple, but it actually isn't, because we'll just say equals x, because we don't have a base 5 in option on our calculators. No such option. So here's what we do. Let's say we're presented with, let's say we're presented with the problem of y equals the log in any base of x. And what we want to be able to do is we want to be able to evaluate this, evaluate the log in any base, evaluate the log in any base, on any calculator, or any calculator that has logs, any calculator. So how do we do this? Well, what we're going to do is we're going to just start by using what we've learned. We have, let's start with this. We have y equals the log base b of x. So we know if this is true, then we also know that b raised to the y equals x. This is also true. Now here's where we're going to try something that we haven't done yet. We're going to take the log of both sides. So I'm going to take the log, and I'm going to just use just the common log, base 10, and we can also do this with the natural log. Either would work. So I'm going to take the log of base of b to the y, and I'm going to do the same thing on the other side. We'll take the log of x. Now, using the property that we just learned in the last lesson, we know that we can take and put this y out in front, and we can write this as y times the log of b. This equals the log of x. And now the log of b, we don't know what it is, but it's just a number. Just like if I had y times 3, I would divide both sides by 3 to find what y is. So let's just divide both sides by the log in base b. And what we have is the log of x divided by the log of b. And you can repeat this process with the natural log, and you can have y equals the natural log of x divided by the natural log of whatever base you're in. So, is this really true? Well, let's try this. And would we get the same? Well, let's try that too. This is called the change of base. Change of base formula. Now, let's remember where we started. Our motivation was we wanted to take the log in base 5 of 10. So let's return and see how this works. We're going to use our change of base formula. And so if we have the log in base 5 of 10, according to what I've just written here, I can do this by taking the log of 10 and dividing it by the log of the base, which is 5. And if what I said is also true again, we could also do this using the natural log of 10 divided by the natural log of 5. And okay, according to what we just proved, this should work either way. So let's try this. I'm going to go to my calculator and let's see what happens. So I'm going to take the log. We'll just use our common log. So log base 10, mine has the big 10 on it. But log base 10 of, we said 10, and we're going to divide it by the log of our base. So log base 5, and I get 1.430, and the number continues. Now I claim that it works with the natural log. Let's try that. So if I take the natural log of 10 and we divide it by the natural log of the base, which was 5. Okay, here it goes. This would be in a movie. We'd have like a big drum roll scene here to see if this is really true. And sure enough, look at that. As a matter of fact, it would even work with this log base 2 button. Log base 2 of 10 divided by the log of the log base 2 of the base, which is just 5. And look at that, it works again. And so that empowers us now that we can take the log of any number in any base. I hope that helps. Thanks for watching.